This slide basically lists all the formulas we need to deal with the MM1 queuing model. So for MM1 queuing model, the first thing you need to do is to identify two pieces of information. The first piece of information is the mean arrival rate. So basically, how many customers coming into your system per hour, arrival rate. So how many customers per hour, arrival rate. Second piece of information you need to identify is by reading the question, you need to identify the mean service rate. So basically, how many customers you can serve per hour. This is how lambda is how many customers come into a system per hour. Mu is how many customers you can serve per hour. So we need to identify these two pieces of information first. So right after that, you can calculate rho. Rho is equal to lambda divided by mu. This shows average-wise how many customers you will be observing in service. So how many customers are being served on average. Then depends on what question, depends on specific question, you use specific formula to answer questions. So there are three types of questions. The first type of question asking you about a probability. So whenever you see probability, you will have to use these two formulas. Either the probability of exactly n customer in the system, then we use the first formula. Sometimes the question asks you the probability that there are k or more customers in the system, then you use second formula. So anytime we see probability, or sometimes you may see different wording, it's called percent of time. So percent of time or probability, we use these two formulas. It depends on specific question, either use the first one or the second one. If the question asks you exactly n customer, you use the first one. If the question asks you there are k or more customers, then use the second formula. The second type of question we might see is asking you the number of people. So there are two kinds of questions. You can either see the number of people in the system, so which is LS, the number of people, LS in the system. The second type of question you might see is the average number of customers in the queue. So L is a customer, Q means in the queue. So you either see LS or LQ. LS is the average number of people in the system. LQ is the average number of people in the queue. So it depends on what question you use different formulas. The last type of question we might see is that in terms of time. So there are two types of questions. So one is the average time in the system, so which is WS. S stands for system. The second type of question is average time in the queue. So how much time does each customer spend in the queue? This is how much time does average customer spend in the system, including waiting time plus survey time. This is only the waiting time. So WQ is the only waiting time. WS is that the waiting time plus the service time. So WS is always longer than WQ. So again, there are three types of questions. One is talking about probability, these two formulas. The second type of question asks you number of customers, either in the system or in the queue. The last type of question is talking about time, either the time in the system, WS, or time in the queue, WQ. So these are the formulas we might be able to use. So now, let's go to exercise question 2. So exercise question 2, you can follow example 13.2, which was covered in class. So let's read the question. So first of all, the mean arrival rate is 10 boats per hour. So 10 boats per hour is the mean arrival rate. Basically, in other words, this says lambda. This is lambda. Lambda is 10 boats per hour. So as I mentioned, in order to deal with MM1 model, we have to identify two pieces of information. One is lambda, one is mu. Let's look at second piece of information. It says launch time follows exponential distribution with a mean of 4 minutes per hour. So look at this, 4 minutes per boat. 4 minutes boat, is that mu? Mu should be interpreted as how many customers per hour. This is how many 4 minutes per boat. So this is not mu. Okay, this is not mu. This is a service time. To serve one boat, it takes 4 minutes. Okay, to serve one boat, it takes 4 minutes. mu is how many boats we can serve per hour. So 4 minutes per boat is not mu, it's not service rate. This is a service time. So we have to do something to convert 4 minutes per boat to how many boats we can serve per hour. So as I said, lambda is 10 per hour. So arrival rate is 10 boats per hour. So given it takes 4 minutes to serve one boat, so we want to figure out how many boats we can serve per hour. So it's 60 minutes. So we have 60 minutes in 1 hour. It takes 4 minutes to serve one boat. So 60 divided 4, we have 15 per hour. So 15 per hour is a service rate. So basically we can serve 15 boats per hour on average. So now we know mu, lambda, we know mu, we can easily calculate rho. So rho is equal to lambda divided by mu, which is 10 divided by 15, is 2/3. 2/3. That shows on average how many customers are in service. So let's answer the 6 questions. The first question, what is the probability that the system is busy and arriving customer waits? So probability, first of all, it's probability. So that's the first type of question, probability. So what is the probability that system is busy? What does it mean? System is busy, what does it mean? System is busy means there is at least one customer in the system. That means system is busy, right? If the system has 0 customer, that means system is not busy, it's idle. So here, talking about system is busy, that basically it's equivalent to say that the system has at least one or more customers. So how likely you will see one or more customers in a system? So we can apply the formula. So what is the probability that you have more than one customers, which is rho equal to 2/3, which is, if you do the fractional number, it's 0.667. So it's about 66.7% time the system is busy. So reading the question is very important. Understanding what the question is asking about is very important. Then we can apply the right formula. Second question, what is the probability that the system is idle? So again, this is talking about probability. So this is the first type of question, probability question. So for probability question, we have 2 formulas we can use. So let's read the question again. So how likely the system is idle? The system is idle, what does that mean? The system is idle, that basically means there is a 0 customer in the system. When there is 0 customer in the system, then the system is idle. So the question is basically talking about how likely the system has a 0 customer. So this is the formula. How likely n is equal to 0. How likely there are 0 customer in system, exactly 0 customer in system. So we can apply the right formula, we plug in the number, we'll get 0.333. So basically there are about 33.3% time or likelihood that the system is idle. Next question, what is the average number of boats in a system? Average number of boats in a system. Average number of boats in a system. So what is this about? We go back and think about all the formulas we have in the previous slide. Average number of boats in the system is asking about what? It's talking about number of customers in the system. So this is really talking about LS. L is number of customers, S in the system. Number of customer in the system, average-wise. So this is the right formula to use. So once you figured out the question is about LS, the rest is pretty straightforward. So LS is equal to lambda divided by mu minus lambda. We plug in all numbers, we'll get 2. So on average, you will see 2 boats in the system. So number of customers in the system. Next question, what is the average number of boats in the queue? Average number of boats in the queue. Average number of boats in the queue, basically talking about average number of customers in the queue. So what is that? Average number of customers in the queue, which is a LQ. Customers, number of customers in the queue. So equal to rho times lambda divided by mu minus lambda. So we plug in all these numbers to get 1.333. So average-wise, we will see 1.333 people or 33 boats in the queue, average-wise. Average-wise, we have 2 boats in the system and 1.333 boats in the queue. The next question, question 5. What is the average time in the system? So average time in the system, what is that about? Going back and thinking about all the formulas, average time in the system, this is really about WS, okay? Average time in the system, WS. So WS equal to 1 divided by mu minus lambda. So we plug in the number, so which is that 1/5. Now here, be careful. So how do we interpret 1/5, 1/5, 1/5? What does that mean? Because both mu and lambda this is service rate, lambda is arrival rate. So both are per hour rate, okay, per hour. Because both are per hour rate, when we do the calculation, we got a number. This number should be interpreted as how many hours to be consistent. Because both lambda and mu are per hour, so the result should be interpreted as how many hours. Of course, you may not like it. You may not like 1/5 hour. What does that mean? So we can convert to minutes if you like. So 1/5 hour times 60, which is 12 minutes. So it's equivalent to 12 minutes. So 1/5 hour is equal to 12 minutes. So average time in a system is 12 minutes. So average-wise, a boat will spend about 12 minutes in a system. The last question, what is the average time in the queue? Average time in the queue. What does that mean? If you think about the formulas we just discussed on the previous slide, this basically means what is WQ? Average time in the queue, WQ. So this is the right formula. We plug in all the numbers, we get 2/15. Okay, 2/15. Again, this is similar because both mu and lambda are per hour rate. So this number should be interpreted as how many hours. So it's 2/15 hours. So 2/15 hours, we can convert this to minutes if you like. So 2/15 times 60 minutes, so you get 8 minutes. So average-wise, each boat will spend 80 minutes in the queue and 12 minutes in the system. Of course, you can see this is longer, right? The time in the system is equal to time in the queue plus time in service. That's why the timing system, WS, is longer than WQ. So next question is exercise 3. So for exercise 3, you can follow example this about Sunset Airlines, which we covered in class. So based on that, you can practice this. So what I suggest you do is to try on your own, to read the Sunset Airlines example, which was covered in class, and try on your own first. Then you can take a look at the solution, how I did it. So let's read the question. So first of all, the mean arrival rate is 12 passengers per boat per hour. So obviously, this is that arrival rate is 12 passengers per hour. Second piece of information, a single clerk spends an average of 4 minutes per passenger. 4 minutes per passenger. Is this service rate or service time, right? So what is service rate? We want a service rate. We need a service rate. Service rate is how many customers you can serve per hour. Right? This is each passenger requires 4 minutes to be served. So 4 minutes per passenger is simply service time. It's not service rate. So that means we have to convert. We have to convert this information into how many passengers we can serve per hour. So let's answer the question. First question, what is the probability that an arriving passenger will be served immediately without waiting? So first of all, before we answer this question, as I said, for any MM1 waiting line model, so we first have to identify lambda, we have to identify mu, we have to calculate rho. So what is lambda? Lambda is easy, it's 12 customer per hour. Mu is not given, so we have to do convert. So what we know is each passenger will have 4 minutes per passenger. So we have to convert 4 minutes per passenger to how many passengers we can serve per hour. So 60 minutes divided by 4 minutes each passenger, we have 15 per hour. So 15 per hour is the service rate. Now we know the arrival rate, which is 12 per hour. We know the service rate, which is 15 per hour. We can easily calculate rho. Rho is lambda divided by mu, which is 0.8. Now we can answer the first question. So what is the probability that an arriving passenger will be served immediately without waiting? What does that mean? First of all, it's a probability problem. It's a probability, so it's the first type of question. So the probability about what? About arriving passenger will be served immediately without waiting. So basically means how likely you will see 0 customers in the system. If there's 0 customer in the system, that means a new passenger will be served immediately. So this is the same question, okay? The question says how likely arriving passenger will be served immediately, which also means how likely there will be exactly 0 customer in the system. So once you understand this, to solve it, it's pretty straightforward. So we know we want to figure out probability. The probability that there is 0 customer, n equal to 0. So this is the right formula. If you go back and take a look at the previous slide, you can see this is the right formula. You plug in the right number. Rho is 0.8, so we get 0.2. So it's 20% chance that system has 0 customer, which also means a new arriving passenger will be served immediately without waiting. A second question. The area in front of counter can only accommodate 4 passengers because this room has some capacity. So the area can only accommodate 4 passengers, including the one being served. So basically means you can serve 1 passenger plus 3 people waiting. Only have 3 spaces to serve, to accommodate 3 waiting passengers. And then plus another one is in service. So altogether, we can accommodate 4 passengers in the system. So here, what percent of time will this area be inadequate for waiting passengers? Inadequate for waiting passengers. First of all, it's a percent of time. As I said, a percent of time, it's also equivalent to probability. So percent of time or probability, same question. Okay, percent of time, probability, same question. So this is first type of question asking you about probability. So this is probability about what? The probability that the area is not adequate. The area is not adequate for waiting passengers. So the area can only accommodate 4 passengers. Here, when the area will be inadequate for waiting passengers, of course, when there are more than 5 passengers, right? Because you can only serve, you only have enough space to serve 4 passengers. So when there are 4 or more passengers, this area will be inadequate for the waiting passengers. So basically, this question asking about how likely there will be more than 5 passengers in the system. So inadequate space, same thing as more than 5 passengers. So probability that you will see more than 5 passengers, which is rho to the 5th power. If you do the math, you get 0.328. That's about 32.8% time the area will be inadequate for waiting passengers. That means you will lose customers. The last question, question 3, we need to add another clerk when passengers begin to experience an average wait time, an average wait time of 30 minutes, determining the arrival rate that indicates the need for another clerk. So far, for all the questions we deal with, we know lambda, we know mu, then we calculate something else, right? This question is a little bit unusual. So the question asks you about determining the arrival rate. So we want to figure out the arrival rate, okay? So mu is given. Mu is given, but arrival rate is not known. We also know what? The target average wait time is 30 minutes. So wait time, 30 minutes. We know wait time, 30 minutes. We know mu service rate. We want to figure out what is arrival rate, lambda. So this is a bit unusual question. So typically we know lambda and mu. We try to figure out something else. In this case, we don't know lambda. We have to solve for lambda. So what formula do we use? Here we're talking about wait time. So average wait time. So what is average wait time? It is a WQ. So we use the formula WQ equal to rho divided by mu minus lambda. So in this case, mu is a lambda is unknown. Okay, lambda is unknown, but WQ is known. WQ is 30 minutes. This is our target average wait time. So lambda is unknown. So mu is 15. That's the same, 15. So rho is lambda divided by mu, which is 15, and then also have mu is 15 minus lambda. So this whole term is equal to the average wait time is about 30 minutes. The reason I did 30 divided by 60 is for consistency reasons. As I said, in this formula, when we apply the formula, both mu and lambda are per hour rate. That's why in terms of average wait time, we have to use how many hours. So the given information is 30 minutes. So we don't do 30 here because 30 is not the right number. 30 means 30 minutes. We want the average wait time of how many hours. So 30 minutes is equal to 30 divided by 60 hours, basically half an hour. So now we have this formula set up. So we don't know lambda, but we do know WQ, which is 30 minutes or half an hour. So given this equation, we can solve it. We solve for what? Solve for lambda. So you do the math, you get lambda equal to 13.24 per hour. So this is our estimate arrival rate. So whenever the arrival rate reaches to this number, then customer will begin to experience an average wait time 30 minutes. That means we may need to add another clerk